Hey team, welcome to our final video of Science 10. I can't believe we made it here. This is the last topic I have to teach you about. It's crazy. What a wild and bizarre year it's been. But here we are in our last lesson, and I hope that you guys aren't crying as hard as I am right now. I am just stifling my emotions. Anyway, today we're talking about one of my favorite topics in physics, which is the concept of efficiency. Which is funny because I'm putting this video up later than I wanted to, which means I was not being very efficient when I made it. Either way. So efficiency is a physics concept that comes out of the fact that the world is not perfect. So when I gave you guys the mechanical energy video today, I talked about how however much energy you start with has to be the amount of energy you end with, and which is true. But I kind of lied to you in terms of what type of energy that is, because it turns out that however much energy something starts with is not always how much energy that particular object keeps over the course of its movement. Which brings us to the concept of efficiency, which is how well an object uses all of the energy it began with. All right, so we're going to do this. We're going to start out with an example here. So let's imagine that I have a ball with a mass of 0.40 kilograms, and it rolls up a ramp with an initial velocity of 3.5 meters per second. The ball stops rolling when it reaches the top of our 0.35 meter tall ramp. And the question says calculate the starting kinetic energy and then the final potential energy. So this is not by itself an efficiency question. It's not telling me, hey, or asking me what is the efficiency of this ball or this ramp or whatever. It just asks me to calculate these two things. So let's go through this together. Let's start with the kinetic energy that it starts with. So this object, we want to know its kinetic energy. We know its mass is 0.40 kilograms. And we know its initial speed is 3.5 meters per second. Perfect. So we're going to use our EK equals mv squared divided by 2 formula. We're going to throw our numbers into that. So we're going to go 0.40 kilograms times 3.5. I'm just going to zoom out a little bit. 3.5 meters per second squared. And we're going to divide that by 2. And when I plug that in my calculator, I get 2.45 joules. Perfect. All right, so now we want to calculate the potential energy that this thing ends up with. So the potential energy is what we're trying to find. We still know the mass. It's still 0.40 kilograms. We know that the gravity is always 9.81 meters per second squared. And we know that the height, in this case, is 0.35 meters. So as we try and find our potential energy, we're going to go EP is equal to mass times gravity times height, which in this case is 0.40 kilograms times 9.81 meters per second squared times 0.35 meters. You know I don't have enough room to write this, so I'm going to just back it up even further. 0.35 meters. Okay? And when I multiply all that together, what I get as an answer is 1.37 joules. All right? Now, I know what you're all screaming back there is I don't have the right number of significant digits. This should be 2.5 joules. This should be 1.4 joules. Perfect. That's all fixed. So the thing that the issue that we have here, as soon as you get these two answers, that's different than everything we saw in mechanical energy, is that the amount of energy I started with, this ball rolling, is not the same as the amount of energy it ends with. So the question becomes, where did that energy go? The law of conservation of energy, as we talked about earlier today, says that energy can never be created or destroyed, which means that this energy didn't disappear. It didn't just suddenly vanish into nothingness. That energy became something. It would have had to turn into another form of energy because energy can't be created or destroyed, but it can change form. And while some of this energy turned into potential energy, Obviously, 1.1 joules of it didn't. 1.1 joules of it became something else. So the question is, what would it have become? And if you think about rolling a ball up a ramp, what you have to realize is as you push that ball up the ramp, the ball is rolling against the ramp itself, which sounds like a stupid thing to say. Who cares? We know that when you roll a ball, it rolls. Great observation, Mr. Barry. But it turns out that when that ball is rolling, it's creating friction. It's rubbing up against the ramp itself. And so as a result of that, some of the energy that we put into this ball, the 2.5 joules, some of that is needed to overcome the force of friction. Because friction is energy. It is energy that two moving things have as they rub past one another, which creates heat. So it turns out this extra bit of energy that we started with, that we didn't end up with, would have become heat as the ball rolls against the ramp. And this is where efficiency becomes important, because efficiency, as I said earlier, is how well the ball or the object or whatever it is we're talking about takes the input energy and how well it converts it into output energy. In this case, a ramp is always trying to turn kinetic energy into potential. It's trying to turn speed into height, right? And so as a result, some of the energy that we started with doesn't end up in that height. Some of it was used to overcome friction. So it turns out there's actually a lot of interesting thermodynamic properties of energy. So we talked about, energy can be created or destroyed, great, but it can change forms. It turns out that every single time that an energy does transform from one form to another, some energy is always lost as waste. What I mean by that is some energy is always used to do something that device or that machine or that you didn't mean it to do, okay? Waste energy is usually found in the form of heat. Sometimes waste energy can be sound. If you think of somebody slamming on their brakes really hard to avoid a stop, what's happening there is the friction is so high that there's a huge ton of heat created as the brake rubs up against the tire, but sometimes sound is created because there's so much energy as that brake presses up against the wheel, all right? So waste energy is typically heat. Other times you'll find that it's sound or light, but you need to think about the purpose of the machine and what it is we're trying to use it for, and then from there, what energy does it produce that we don't want? My favorite way to think of wasted energy is your cell phone. When you have a cell phone and you're using it, when you think about what is the useful energy that comes out of a cell phone, it's sound and light. That's it, right? We want it to entertain us. We want to hear the person we're talking to. We want to see the person we're talking to, whatever it happens to be. Even if it's a video game you're playing, you want to hear the sound, you want to see what's happening. So the useful energy is the light and the sound that phone produces. But the more you play a video game or the more you talk to somebody over FaceTime or whatever, the hotter your phone gets. And the reason that's happening is the battery is producing a ton of energy to power the light and the sound of your phone. But not all of that energy that the battery is producing goes to create light and to create sound, because there's friction as those electrons move throughout your phone. And some of that friction creates heat, which is why your phone warms up when you use it. That's why that's wasted energy, okay? So efficiency is how a machine turns input energy. In the case of your cell phone, it would be the battery. In the case of the ramp, it would be the kinetic energy it started with, into useful, and that's the key word there, output energy. What does it turn that energy that we want, how much energy do we get out of it compared to how much do we put into it, all right? So efficiency is a big topic in how we design things today. So an LED light bulb, which are the more common type of light bulbs now, they're 40 to 50% efficient, which doesn't sound very much. But incandescent light bulbs, which came before LED light bulbs, were about 10% efficient. They actually created light by heating up a piece of metal so much that it it lit up. Anyway, point is, they were super inefficient. They wasted a ton of electricity because 90% of the electricity that went into it was used to create heat rather than to create light. The light bulbs we have now are much more efficient than that, but still not very efficient. When we talk about something being 40% efficient, what that means is of all the electricity coming into it, 40% is being used to create light. The other 60% is being turned into heat or something that we don't want from that particular object. Okay? A car engine is one of the most inefficient machines that we still use to this day. A car engine is about 20% efficient, so 20% of the energy that's in gasoline is actually used to make the car go forward. The other 80% is turned into heat, which is why cars have whole systems devoted to them to take heat away, to stop the car from overheating, right? So let's take a second and think about how efficient was the ramp from the slide before this. Now, to figure that out, we're going to get our last formula of the entire Science 10 year, which makes me so happy. We don't have to learn any more formulas. And it's this formula right here. The efficiency of a object or a machine is equal to its output energy, useful output energy, I should say, divided by the input energy. So how much energy did I give the machine versus how much did it give me? Okay. And then from there, we do that division and then we multiply by 100%. It's the same way we calculate grades in any course, where input energy is the same as like the total that the test could be out of, the best it could possibly be. And output energy is how many you got right, how much of it was turned into useful things. So if you ever want to know like what was my percent on that quiz, you go how many you got right divided by the total amount of questions. If you think about it, because energy can never be created or destroyed, the amount of input energy is going to be the maximum amount of energy that object has. So we go however much it gave out versus the maximum it could have had times 100%. That's how we find efficiency. So let's do that for our ramp that we talked about 2 slides ago. All right, so these are the numbers we got from our ramp calculation. Now we're going to figure out our efficiency of this ramp. So the amount of energy the ball started with was 2.5 joules of kinetic energy. By the time it got to the top of the ramp and then stopped, all of that energy was turned into potential energy. But some of it was gone because of friction. So to figure out the efficiency, we're going to go our efficiency, and there's no symbol for efficiency, which is kind of a pain because now I need to write out the whole word. So our efficiency is equal to the output energy divided by the input energy. So the biggest challenge here is deciding which of these is the input and the output. It's really simple. Number one, no machine is more than 100% efficient, which means that its output energy should never be bigger than its input energy. Otherwise, that machine is somehow creating energy, which can't happen. All right. So my input energy here is going to be 2.5 joules. My output energy is how much the machine put out, which is going to be the 1.4 joules. If you're ever not sure how to set up this formula, the lower number should always be on top. The higher number should always be on the bottom. And then I'm going to multiply that by 100%. And when I put that in my calculator, what I get as an answer is 0.56, which when I multiply by 100% gives me a total efficiency of 56%. In other words, this ramp takes 50% or 56% of the energy it started with and turns it into height. The other 44% of energy was used to overcome friction. Now let's look at an example problem together. This one's not in your book. In fact, there's no efficiency stuff in your book. You're going to need to use the online material I provided you to find this. But this one here talks about a car. So it says the chemical potential energy in a car is 5.60 times 10 to the power of 8 joules. If the car uses this gasoline to move forward with a kinetic energy of 1.2 times 10 to the power of 7 joules, what is the efficiency of the car engine? So the only trick to these types of questions is to figure out what is my input energy and what is my output energy. And so knowing that our formula is efficiency is equal to our output energy divided by our input energy times 100%, knowing which is our output and our input is super important to us. There's 2 ways to think about it. Easiest way is to think about the input energy as being whatever energy the object starts with. All right. In this case, we have this much gas in the car, and then we're going to use that gas to get this much energy out of the car. So this is our input energy. This is our output. You can think of it as a time. If you're really not sure, if the question's confusingly worded, always remember that the smaller number is going to be our output, and the bigger number will be the input. If you ever calculate efficiency and you get a number bigger than 100%, you've done something wrong. No machine in the world is more than 100% efficient. Otherwise, it's creating energy, which would basically totally change how life works on this planet. All right. So what we're going to do is we're going to take our two numbers here. We know that this smaller number is our input energy. So what we're going to do is we're going to go 1.2 times 10 to the power of 7. Put that in brackets in your calculator. Divided by 5.60 times 10 to the power of 8 joules. And again, put that in brackets in your calculator. And we're going to multiply that by 100. When we do that, what we get as an answer is, what I get as an answer there is 2.1 percent, right? Remember that with efficiency, we're always finding a percentage. There's no unit to calculate there, it's just a percentage. So this car is only 2.1% efficient. Its engine only turns 2% of the energy from the gasoline into actual forward movement. The other 98% is used to overcome friction. It's used for the parts of the car to rub against each other. So that's how we find efficiency. I have posted a worksheet on D2L that you guys should do to get extra practice with these types of questions. But the overall idea of efficiency is pretty clear. It's just how well does an object turn its output or input energy into output energy. That's it for me for today. I hope you guys have a great day, and I will see you tomorrow on our online class.